morning, this is Miss Billerbeck, and we're going to talk about 17.1, Probability of Simple Combined Events. So, in order to organize simple combined events, a possibility diagram is an amazing tool. It's a rectangular grid that represents the sample space of a random experiment involving two stages. So this is very critical, two stages. So things like tossing a coin twice or two different coins at once, or rolling two dice at once, or selecting two letters from a given word, those would be two events. So here's a rectangular grid that we can use. So it looks like an XY diagram, and we can combine these just similarly like coordinates, but we don't use parentheses or commas. We just write EW. And this one would be EI and EN. So this one we would have RW and RI and RN. And here we would have UW, UI, and UN. And this top one, we would have SW and SI and SN. Okay, so the SN combines here. So then we look at, well, what is the sample space? So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And a simple way to count would have been 4 times 3, which is 12. So we have 12 in our sample space. So now we have to look at two vowels. Well, two vowels, well, let's look at that. So vowels are A, E, I, O, U. So anything with S's are out. This is possible because that's a vowel. So we have one vowel, double vowel here. Anything with an R is out. And then we have another double vowel here. So we have two. Okay, so now we look for a W. So let's see, let's use purple. Okay, so this whole column has a W. So we're going to write that. So the W is 4. So when we look at, well, what would the probability of two vowels be? That's going to be this number, 2 over the sample space 12, which reduces to 1/6. So we can just leave that as a fraction. So the probability of W, well, there's 4 occurrences of W out of 12. So that would be a probability of 1/3. All right, so let's look at this one. So we have two fair-sided dice, or we could say a 6-sided number cube, are rolled. So this is going to take a little time here. So we're going to look at how many there are. So we have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then this is 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Then we have 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and finally the last row, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So now we have the sample space here. So again, we could just multiply 6 times 6 instead of counting them all, and that's 36. So the sum is 6. Okay, well, let's go circle those things that are the sum of 6. So we have this is the sum of 6. 2, 4 is the sum of 6. 1, 5 is the sum of 6. 4, 2 is the sum of 6. And 6, 5, 1 is the sum of 6. So the sum of 6, we have 1, 2, 3, 4, 5. So there's going to be 5. Let me use a darker pen so you can see that. 5. All right, so if we're going to look for doubles, well, doubles we have right here. 1, 2, 3, 4, 5, and 6. So there's 6 doubles. So now if we look at the probability, the sum is 6, we have 5 over the total sample space, which is 36. Now this we can't reduce, so we can leave it as a fraction. And the probability of doubles is 6 over 36, which is 1/6. So that would be the probability of rolling doubles, 1/6 of the time. So just for giggle's sake, let's look at what percent 1/6 is. So that's 17% of the time. So it's 0.17, which is 17% of the time. And 5 divided by 36 is 0.14, which is 14% of the time. All right, your book doesn't go that far with the percents, but it's a good thing to practice. The next thing we need to talk about is the tree diagram. So if a random experiment consists of 2 or more stages, we can use a tree diagram to represent the process. So a coin toss would be represented like this, where our first coin could be a heads or a tail. The second coin toss would be a head or a tail, or a head or a tail, depending on whatever this first toss was. And then the third toss of the coin, again, is head or tail, head or tail, head or tail, and head or tail, but it comes off of each one of these other possibilities. All right, so let's look at what are these outcomes. So this outcome up here was H, H, H. So we went from H, H, H. And then we had H, H, T. And then this branch we had H, T, H. And H, T, T. And this branch we had H, or T, H, H. And T, H, T. And then this branch was T, T, H. And T, T, T. So these are all the possible outcomes. So we count them. We have 1, 2, 3, 4, 5, 6, 7, 8, which would be the same as 2, 4, 6, 8. So we have 8. So we look at all the possibilities of HTH. Well, the only one is right here, HTH. So with that, we have 1. There are no other HTHs. Okay, the number of possibilities of TTT, whoops, I missed, that one was not right. That was a T, is right here. So there's one. So one outcome of TTT and one outcome of HTH. So the probability of HTH would be 1/8, and the probability of TTT would be 1/8. But what if I changed this and said the probability of 2 H's and 1 T instead of HTH, where order did not matter? Then we're looking for something that has 1 T and 2 H's. And then look at that. There are now not just one, but there are 3. If it didn't matter the order. So then that would change this to a 3/8. Okay? So we have to be careful about how they're asking for these combinations. Does order matter or does it not? All right, let's look at a family that is having a baby. And they don't know what sex it's going to be, whether it's going to be a girl or a boy. So, and they're good planning on 2 children. So one could be a boy and one could be a girl for the first child. Okay, the second child, these are mutually exclusive events because each pregnancy is exclusive. So this could be a boy or a girl. And this could be a boy or a girl. So that would be the second child. All right. So if we look at that probability and list these out, we would have BB, BG, GB, and GG. So the number in our sample space, the number of outcomes is 4. So the number of outcomes of boy, boy is 1. And the number of outcomes that are boy, girl, or girl, boy, well, we have 2. So when we organize that together, we have 1 over, and we have 4 in our sample space. So 1/4 of the time you'll have a boy, boy, and that's 25% of the time. A boy, girl, or a girl, boy is 2 out of 4, which is 1/2, and that's 50% of the time you'll have that. Okay, so what if we have a larger family and there's 3 children? This gets interesting. Okay, so let's see the probability of having 3 boys or 3 girls. Okay, so we have the 3rd child. Okay, so now let's organize our sample space here. We have boy, 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 girl, boy, girl, boy, and boy, girl, girl. Here we have girl, boy, boy, and girl, boy, girl, and girl, girl, boy, and girl, girl, girl. So if we count that sample space, 1, 2, 3, 4, 5, 6, 7, 8. So our sample space now has 8 possibilities or 8 outcomes, and our number of outcomes that are boy, boy, boy is 1. But what about the number of outcomes that are with just one girl? So if we have only one girl, that would be this one, that one, and are there any more? That's it. So we have 3 outcomes with just one girl. So in this case, our probability of BBB is not very likely. It's 1 out of 8. So that's about 13% of the time. Okay, the probability of one girl is 3/8, which is about 38% of the time. All right, so there you have it. It's not very likely to have 3 boys out of 3 children. And the same would be true for 3 girls. 13% of the time would be 3 girls out of 3 children. All right. So now let's take a look at this. So we have a box A that contains a red ball and a green ball and a blue ball. So let's write out that tree diagram. Let's use this color. Okay, so we have a red ball, a green ball, and a blue ball. Okay, and then we have a box B that contains a red ball and a blue ball. Okay, so we just have a red ball and a blue ball. That makes it easy. And a red ball and a blue ball. All right, let's draw out our sample space. And we have R, B, G, R, G, B, B, R, and B, B. Okay, so the probability of R. Well, we have 1 R occurring out of 1, 2, 3, 4, 5, 6. So that'd be 1/6 of the time. The probability of GG happening, green, green. Well, in the second bag, it contains a red bag and a blue ball. So the probability of GG happening is 0 out of 6. Okay, because it's not one of the possibilities. You can't pick a green ball out of box B. because there are no green balls. So how about the possibility of the same color? So if we look at the same color, that would be this and this. So we have 2 out of 6, which is a third of the time. And the possibility of different colors. So that would be the rest of them. So there's 1, 2, 3, 4. So that'd be 4 out of 6. So that's going to be 2/3. All right, so tree diagrams are a very helpful way of organizing data. And then you're not restricted to just being able to look at 2 events. You can look at 2 or more events happening together. All right, so that's it for section 17.1. Have a wonderful day.